All right, why don't we go ahead and get started? So welcome back everybody to EE240. So just a couple of sort of reminders. The project phase 2 is going to be due this Friday, not Thursday, so I'll give you sort of an extra day there. So that's kind of the good news. The bad news is I'll be posting phase 3 very shortly, probably even before phase 2 is due. Just kind of want to make sure that you guys basically have enough time to actually go ahead and get started on that. In the past, I actually sort of pushed that a little bit later in terms of the due date for phase 3. But because of the way the final got scheduled this year, I don't think I'm going to be able to do that. So definitely make sure you go ahead and get started on that. The other thing I should mention on the project is we noticed on phase 1, a bunch of you guys sort of did it without a partner. That if you're still doing that for phase 2, that's fine. But trust me, for phase 3, you don't want to do that. So make sure you find a partner. It's always good to learn how to work with people because trust me, there's just more than enough work to be done, and you'll want to have somebody that you can work with, kind of bounce ideas off of, and make sure you guys are both sort of going down the right direction. So if you didn't have a partner, make sure you find one for phase 3. If you're not able to find one, just come bug me, and by the way, do that pretty soon so that we can kind of get you set up before all that really gets going in a major way. So any kind of questions on sort of the project or material or anything like that we've been talking so far? How many of you guys are at least started phase 2? Anybody done? Brave souls, okay, good. So hopefully people will be finishing that up very shortly here, because again, that's due this Friday. So, no questions on the project or material or anything like that? Okay, so with that, let's just go ahead and dive back in. So last time we were talking about comparators, and I think where we basically ended up was talking about so-called regenerative latches, where we said that rather than sort of doing a long cascade of a bunch of amplifiers in order to get the gain, it was actually much more power efficient to essentially just take a single amplifier and basically tie it into positive feedback. So what that kind of means is you end up with something that at least conceptually looks sort of like what we had drawn here. And we walked through a little bit sort of what would set the time constant of the regeneration of this, basically, in other words, how long it would take you to get a full swing signal at the output given a certain size signal at the input. So where we had basically ended up was kind of hinting at the fact that this conceptually works just fine, but is a little bit annoying in the following sense. So if we sort of think about it, what we're going to be doing here is, in order to actually get the input signal onto this thing, when we turn these switches on, the input signal is basically just sort of fighting with a cross-coupled latch here, right? So conceptually with real voltage source inputs, that sort of works fine, but probably in practice, given that this may be coming from an OTA or something like that, that may not really be what you want to do, right? You may not really want to be sort of pulling current out of the small, very, very sensitive input signals that you're trying to regenerate. So what I'm basically going to do is walk through kind of a couple of other comparator topologies, which practically speaking will be really what you'll most likely end up using, that we'll see will basically isolate either sampling or amplifying the input from actually doing the regeneration. And by regeneration, I just mean basically tying the thing up into a positive feedback and just trying to decide, okay, was the input signal larger or smaller than some threshold? Okay? So let's just sort of start out by looking at not necessarily the simplest, but one of the simplest so-called latches or regenerative sort of structures that you can come up with. So I'm just going to sort of start drawing this thing, and then we'll go through and sort of see how the thing works. So I'm just going to pretend I have some resistive load. And so essentially what I'm going to do is, in order to sample the input signal, essentially what I'm going to do is in one phase, just connect it up almost like it's just an amplifier. Okay? So of course, once I've sort of sampled the input signal, then what I'm going to want to do is in the other phase, then I'm going to want to somehow basically take whatever that signal was and tie it into this positive feedback loop to basically force it to one of the two, not necessarily rails, but to basically decide one way or the other. So conceptually, the way this is going to look is something like this. So since I basically mentioned that I want to have essentially two phases, that kind of means that essentially based on the clock, I'm going to be deciding sort of which piece of the circuit I'm actually going to be activating. Okay, so I'll just finish drawing this and then hopefully it'll all be clear. Okay, so this is like VO minus, that's VO plus. Okay? So the basic idea here is actually pretty simple. So as I said, imagine that in one phase, meaning when the clock is high, and actually let's go ahead and draw the clock waveform over here. So if that's my clock, then basically, while the clock is high here, essentially I have this path turned on. Okay? So like this transistor here that I'm really just using as a switch, that's going to be off, this one's going to be on. In other words, I have my bias current just flowing through this input differential pair over here. So in that phase, this whole structure just kind of looks like an amplifier, right? So I'm just taking the input differential and basically amplifying it up to get to this output, okay? So obviously, why do I want to do it that way? Well, because basically I'm isolating the input from the output. Then once I'm sort of ready, which of course is based on the clock, once the clock goes low, once I've got some differential input over here, that sort of sets the initial condition on basically the parasitic caps that are sitting right there, then I turn on this switch. So I give this cross-coupled pair some bias current. The cross-coupled pair will see whatever that initial voltage difference was and start regenerating it, right? In other words, it'll go into the positive feedback and basically slam that to one of the two quote-unquote rails, okay? So in other words, if I sort of look at the way the circuit works, when the clock is high, I'm basically amplifying or sampling the input signal. And when the clock is low, that's when I'm going to regenerate the output. Okay? And again, by regenerate, I really just mean tie it into this positive feedback loop. Okay? So actually, conceptually pretty straightforward. And now, as I had mentioned before, the good news is I never actually draw any current out of my input. Right? So my inputs are buffered by sort of that first phase of operation. So by the way, this whole thing is called a CML, which just stands for current mode logic comparator. It's also sometimes called a CML latch, because back when people sort of did logic with bipolar transistors, you could actually replace all these with essentially bipolars, and this was typically how they would actually build latches, like digital latches. Because you can kind of think about it, right? When the clock is high, the input just sort of propagates to the output. In our case, since it's an analog signal, it propagates to the output with some gain. And when the clock is low, that's when you sort of just store the output. In this particular case, storing the output actually means that we regenerate it out to the full swing. But kind of the same idea, right? Okay, so just a couple sort of quick things to notice here. So again, this actually works reasonably well. It's a pretty straightforward design. And when we get to phase 3 of the project, which again will be very soon, I'll actually be giving you this particular comparator design to use. That's not necessarily because this is the best possible comparator you can build, but it's a lot easier to analyze, particularly from a noise standpoint, than some of the other comparators that we're going to talk about in a second. Okay? So I'm going to give you that comparator. You should sort of feel free to use it, but obviously one component of the project is for you to kind of go in and figure out how you can do some additional optimization on it. So one of the other things that is sometimes not particularly desirable from this design is that if I actually look at these differential outputs over here, remember in a comparator, you're kind of like eventually trying to get digital outputs that are either ones or zeros, right? Now when we say 1 and 0, that doesn't necessarily mean anything about what the voltage swings actually are. But usually if we wanted to like feed this into a CMOS gate or something like that, 1 and 0 usually means VDD and ground. Well, so in this particular design here, unfortunately, the outputs don't really swing from VDD to ground. So what do they swing between? What sets the sort of swing in this particular circuit here?
IR over 2.
Okay, so you said IR over 2. Let's maybe, just start it out a little bit simpler. So if I'm going to get a quote-unquote 1 on the VO plus side, what would be like the voltage level at the output from VO plus?
VDD minus I bias.
If I got a 1.
Oh.
You almost gave me the answer to the next question,
Yeah.
but
V star.
so if VO plus is going to be a 1.
VDD?
Yeah, it's just VDD, right? Because basically if it's going to be a 1, that essentially means that this transistor over here is off, right? In other words, I have no bias current flowing through that side. Okay, so basically I'm going to have VDD, and if VO plus is supposed to be a 0, that's when I'd steer all of the bias current onto that side. And so as Will was sort of saying, it's just going to be VDD minus IB times RL, where of course these are the RL. Okay? So basically, it works. It's going to give me sort of things that'll be either VDD or VDD minus IB times RL. But it doesn't give me like full digital outputs, meaning it doesn't go all the way from VDD down to ground, right? And so a lot of times, again, if you want to use the output of this comparator, you want to feed it into some CMOS logic. So sometimes this is a little bit annoying because you have to add like another circuit afterwards that takes that smaller swing and converts it to a full CMOS level. Okay, so as I said, I'm going to be giving you this comparator, and from the standpoint of the project, you don't need to worry too much about whether or not it really goes full swing or not. But from a practical standpoint, that is something that you will typically care about. Okay? So in order to see how we can build comparators that sort of still have some of the same functionality, meaning they will grab the input signal without causing any current to flow through it, and then sort of regenerate it, what I'm going to take a look at is actually a comparator design that originally came from actually digital guys. Okay? So this thing is called a strong arm latch, and I'll draw sort of what it looks like in 1 second, because the people who originally came up with it, or really the ones who made it most popular, were the people who were designing the strong arm microprocessor. Okay? So this one, the main difference here is going to be that the output is really going to be full swing. I mean, it's going to have full digital levels. So to see how this thing works, I'm just going to sort of start drawing it, and then we'll sort of see how this structure essentially evolves. Okay, so as you can kind of guess, almost all comparators kind of somewhere inside of them have some cross-coupled inverter built into them. Okay? So this particular comparator is no different. So kind of the core of the comparison is indeed going to happen through some cross-coupled inverter. But by the way, I intentionally didn't draw the grounds here yet. Okay, because what I'm going to do in 1 second is rather than really tying the sort of grounds of these cross-coupled inverters to really ground, I'm actually going to, that's the way I'm going to get my input signal to flow into this thing. So the next piece is actually, again, going to look a little bit funny, but we'll see what's happening here. So I'm going to have VI plus there, VI minus there, okay? And then I'm going to have a clock down at the bottom over here, okay? So what you can kind of start to see already is that the way I'm going to get my input signal into here is basically by modulating the current through these two input transistors. Okay, now actually I'm not really completely done, because to really get this thing to work, you have to sort of start it off from some known bias point. So I'm just going to show sort of how we do that. In this particular case, what we're actually going to do is pre-charge the two differential outputs to VDD. Okay? So again, this is going to be VO minus, that's going to be VO plus. Okay, so now we've sort of actually shown all of the kind of the basics that we need to see how this thing is going to work. So again, I'm just going to sort of maybe, to really see what's going on, I'm going to just sort of draw a plot of the differential outputs versus time. Okay? Okay, so let's assume that initially the clock is low. So as I said, when the clock is low, basically this transistor is off, so there's no like pull down path that's active in this whole thing. These two PMOS transistors are on, so of course both of the outputs will get pre-charged to VDD. Okay? So now, let's say that the clock goes high right at this time. In other words, both the pre-charged devices turn off and this bottom transistor actually turns on. So when that happens, what's going to start happening at sort of these two outputs right here? What does the circuit sort of look like when this clock turns on? Can these outputs stay at VDD? No, right? Because this transistor's on. As long as I have some reasonable input common mode, these two transistors will also be on, right? So I'm going to start basically pulling some current out of the outputs. right? Because just, hey, these two started at VDD, but I have current flowing through those NMOS transistors, so I'm going to start pulling those outputs down, right? So now, here's the million-dollar question. Will those two outputs start going down at exactly the same rate, or will they have slightly different rate at which they go down by?
Different rate.
Yeah, different, right? Why?
I believe VI plus is larger than VI minus, I guess, right?
Yeah, so as an example, let's say that VI plus is larger than VI minus. That means I'm going to have slightly more current flowing through this branch than I do through this branch, right? So if we actually just sketch that, what's going to happen is I'm going to have something that sort of looks like this, right? So the two outputs are both going to go down, but with a slightly different rate, right? And I've actually probably exaggerated it here, but that's okay, okay? So now, initially, both of those are just going to start falling down. But eventually, we know what we want to have happen is that the thing actually regenerates, right? Meaning that we kick into this positive feedback and just force the two outputs to either go to VDD or ground, right? Okay, well, so initially, while I'm pulling the current out like this, right, these PMOS transistors are basically off because as long as I'm up near VDD, their VGS is essentially 0, right? But eventually, when I get sort of close enough to the threshold of these two devices, then the PMOSs will actually start to turn on, right? Once those things turn on, and in fact, actually once these NMOSs also turn on nicely, then this thing just becomes a cross-coupled inverter, right? Once it's a cross-coupled inverter, then it really just becomes a positive feedback amplifier, okay? And when that happens, that's when I basically start to regenerate. So at that point, once I sort of hit this sort of magic threshold, that's when I sort of, and my drawing's not the best here, so let me maybe fix that up. Basically, both of those, once I hit the regeneration phase, then I just basically get the standard exponential settling that we talked about, last time, and even this time a little bit as well. Okay? So in some sense, what's happening here is that first phase where both the outputs are going down, but going down at slightly different rates, I actually claim that that's kind of like an amplification phase. Okay? Because basically you can sort of think about it, if I say that there's a certain amount of time at which I'm going to be just pulling these outputs down before the regeneration kicks in, then basically by integrating those two different edge rates over that amount of time, I'm basically going to be essentially amplifying up whatever the input difference was, right? Once I hit that sort of magic specified time at which I start to regenerate, that's kind of what sets the initial conditions, and then the positive feedback just kicks in, and this time constant here is just set basically by the GM over C. Okay, or kind of like by the FT of this cross-coupled inverter here. Does this make sense to everybody? Or? Okay, so now the thing that's kind of interesting in this particular design is if I look at the clock, right, the clock has been high kind of this entire time here. Right, so this is like the clock waveform. So unlike in the previous design, where the clock explicitly tells you, okay, now you should amplify versus now you should regenerate, in this design here, it's kind of like self-timed. Meaning there's no like explicit signal that tells it when do you switch between amplify and regenerate. It's really only based on basically the thresholds of the devices that it decides, okay, when should I actually when am I amplifying versus when should I actually start to regenerate the output signal, okay? Now, I actually was sort of, a little bit fast and loose here. In fact, if you sort of think about it, these two nodes right here, during the pre-charge, those two will actually also start up at VDD. So the way this thing really works is that initially you actually start pulling charge off of those 2 points. And then only once you get sort of a threshold, basically both of these get to kind of like a threshold voltage, so that these two devices, only then do you really start pulling current out of here as well. But the idea in terms of when you start really regenerating is basically the same. Okay? Now, the nice thing about this is indeed you really will get a full VDD and ground at the output. So you don't have to do anything extra to kind of use this inside of digital logic afterwards. But obviously this is a much sort of funkier, let's say, design to really analyze and understand kind of what's going on. The good news is it's actually not too bad, and if you sort of just think carefully about how these things operate in the different phases, you can actually come up with some pretty reasonably simple sort of approximations for, like as an example, what the effective gain is during this phase and how much noise you'd be accumulating due to that. But if you really, really want to do it right, it's pretty complicated. Okay, because basically the circuit's kind of internally changing states and has very, very different GMs as you go through like the different states there. And so if you really, really want to do it right, you can get into some pretty sort of complicated kind of stuff. If you're interested, by the way, you can talk to Pierluigi. He even sort of wrote a whole paper about this before he got to Berkeley. It's got like 5 pages of math about how you analyze all the different phases and things like that. But bottom line, at least from the standpoint of this class, turns out you can actually use some fairly simple models and get pretty good estimates for sort of what the sort of noise and performance of this whole structure will be. But just user beware, if you use something like this, it is going to be slightly more complicated to kind of analyze and understand than this simple CML structure here. Okay? By the way, there is actually one other sort of nice thing about this particular design, which maybe I'll sort of ask you guys to see if you can figure it out. So here, my power consumption is really just set by IB and basically whatever the supply is, right? How about here? What's mostly setting the sort of power consumed by this particular comparator? Yeah, it's really just the switching frequency, right? There's no sort of like static biasing current. It's all just coming from basically just switching capacitors around. So the power here is going to be something like CV squared F. So one of the nice advantages about this is that it really is sort of like a digital circuit in terms of its power consumption, right? And that means you change the clock frequency, the power goes down very naturally, which obviously is not quite the same as what you get in the CML design. So does this make sense to everybody, or? Okay. So even though we've seen sort of a couple of comparators now, of course, that's not the end of the story, because actually to really characterize these things and really understand how they perform, there's a couple more, let's say, interesting things we need to talk about. The first is hysteresis, which I actually had mentioned, back in the beginning of last lecture. And so what I mean by hysteresis is, again, just somehow the comparator remembers the previous decisions that it had made. So it turns out just about any comparator you can build will have this phenomenon. But it's easiest to see it with a strong arm latch that I just drew. So let's just sort of draw another picture of that latch. Okay? So again, I have the cross-coupled devices up at the top. Oops. Okay, I've got my input pair. Then I've got my tail device right here. Of course, I've got my pre-charge transistors. So that's clock, and that's clock. Okay, so let's actually take a look at these middle voltages right here. Okay? So, and let's, maybe draw the clock waveform in. So let's say this is my clock. Okay? So when clock goes low, and these two PMOS transistors turn on, these two output nodes, I'm just driving them directly up towards VDD, right? So basically these pre-charge devices, they're sort of setting those to hopefully both actually go all the way up to the supply rail. What's going to happen on these sort of middle voltages right here during that pre-charge phase, when this transistor's off and these two pre-charge devices are on? What happens to those kind of like intermediate voltages? What do you guys think?
Floating.
Are they floating, or are they eventually? I mean, they actually sort of are floating, but at least initially, let's say that they both started out at 0 volts, because by the way, that is actually where they end up in the previous phase. Let's say they both started out at 0 volts. So let's actually draw that. And actually, let me do this slightly a little bit different. Let me call that VM plus and this VM minus. Okay? So let's say both of those initially, and I'll just shift the clock over here. Let's say they were both initially at ground. So when the clock goes low, what's going to start happening to those two?
Creep upwards.
Yeah, they're going to start sort of creeping upwards, right? Okay, now what's going to set sort of how fast they creep upwards? Or what's going to set whether sort of which one of them creeps upwards and when? And to draw that, let's actually take a look at the outputs as well. So let's assume that VO plus, VO minus. Let's say VO plus was high and VO minus was low. Okay? So actually, I'll maybe even do that in a different color just so that it's really clear. So let's say that VO plus here is blue. That's blue. Okay? So, and actually I guess I flipped them, so I'll be a little bit more careful. This is actually VO minus. That's actually VO plus. Okay? So, if VO plus was high, out of these two NMOS transistors, which one is initially on and which one's initially off?
Plus one is on.
Yeah, the one over here is the one that's going to be on, right? So that means that this VO plus, the V middle plus, that's going to start going up. But the other one, which again, maybe just I'll do that in a different color so it's more clear, that one's going to sort of initially stay low, right? Because what's going to have to happen is it's going to take time for this guy up over here to get to VDD, right? Okay, so that means that I already have something like, basically this stays low for a while and then starts to come up, whereas the other one initially is going to come up sort of almost right away, right? Now, for those of you guys who either took 141 or, are sort of thinking about this carefully, what's a little bit bad about me pulling these things up the way that I'm pulling them up? In particular, if I look at like this red thing over here, as I get up close to VDD, is it going to still be a nice, linear ramp like this, or is it going to look like something else? What do you guys think? What did we say in 141 is like something you generally did not want to do? Why did we build CMOS gates the way we build CMOS gates?
Try to pass a 1 through an NMOS.
Yeah, exactly. You're trying to pass a 1 through an NMOS, right? So what's eventually going to happen is this thing's going to kind of, sort of lazily approach VDD minus VT, right? At the same time, that blue guy over there, he's going to sort of start going up and also sort of lazily approach VDD minus VT, right? Well, notice, unless I wait a really, really long time, because these two sort of started off at a slightly different time, unless I wait really, really long enough for both of them to go all the way up to where they're eventually supposed to be, I'm going to end up with a small residual difference on those two nodes there, right? So as an example, let's say the clock went back high again right here. Well, I'm going to have some small like residual difference in voltage on that VM plus and that VM minus there, right? Guess what? If I have that difference in voltage, that means that once I start to try and make another decision, I'm going to have to overcome this difference in voltage to actually get the right answer, right? In other words, it's as if, because I previously had decided one way, that's going to create this voltage difference here, and in this particular case, it'll mean that I'm more likely to stay in the state that I used to be in, and not actually flip into potentially the new state that I want to based on the actual new input signal, okay? So in other words, this is really where hysteresis comes from. It's just basically if you look inside of the comparator, there are certain nodes that maybe don't settle to exactly where they're supposed to go to, or that may remember based on what the previous data was, essentially kind of like have some small residual voltage difference on them. Okay? So this is really sort of the source of hysteresis. Now, the good news is there's actually lots and lots of things we can do to fix it. So, what do you guys think? How should we modify this comparator to try and fix this hysteresis problem that we've just been talking about? What can we do?
Short the VMs together.
Okay, yeah, we can try and short the two VMs together, right? That's certainly true, and the way you could do that is with something like this, right? Just have another switch across there. I claim actually even doing that may not be quite good enough. Why do I say that?
On resistance. Or...
Okay, there's some on resistance. It's going to take some time for those things to really be shorted together to each other. There's actually something else, right? So if I have that switch there, all I'm doing is I'm forcing them to be the same.
Nothing stops from making it VDD minus VT. Go about to VDD.
Yeah, well, or to say it another way, even though I'm forcing them to be the same, I don't know exactly where they are. So if there's, for some reason, for some bizarre reason, like maybe there's a little bit of mismatch or something like that, if when I decide one way versus I decide the other way, both of them land at voltage A versus voltage B, trust me, even that will cause a hysteresis. Okay? Because just through the mismatch, the slightly, the variations in both of those voltages will cause some input referred offset. Okay? So what else do we want to add then?
We can just charge those nodes to VDD with two separate PMOS.
Yeah, exactly. We can actually not only force them to be the same, we can actually force them to be a known voltage. Right? So exactly like you said, we can actually add some pre-charged transistors on there to actually force it up to VDD. Now, by the way, even if you do that, again, it turns out you tend to want this middle switch here too. Because, again, if you didn't happen to settle just long enough, then you may have a little bit of residual error between the two sides. So, in fact, typically, if you really care about hysteresis, you actually add all three of these switches. So you try and force them to both be the same and to both be all the way up at VDD. Okay? Now, it turns out there's actually one more spot that has the potential to actually cause a little bit of hysteresis. Can anybody see where it is?
VO plus and VO minus.
VO plus. Well, actually, we're pre-charging the. So actually, you are right. So technically, if I really wanted to be good about things, I should add, and let me flip this over. I should add the bridge switch up over there to force both of those to be the same. That's actually good. There's actually even one more spot.
The source node of the...
Yeah, right, the source node. Right, that source node, right, during that time it's floating, can kind of like, will just float based on whatever the sort of VO plus and VO minus were, the VI plus and VO minus were kind of during the phase where I'm not supposed to care what the input is at all, right? So in fact, I probably even want to do that, right? I probably even want to force the source to be at a known spot, okay? Now, by the way, just in case you think this is unique to the strong arm, CML actually has very, very similar issues, okay? But the bottom line is, anytime you sort of worry about hysteresis, you really have to worry about how precisely can you settle out what used to be essentially either at the output of the comparator or at the internal nodes. Okay? Does this sort of make sense to everybody, or?
Are you pulling the source up or down?
I'm pulling it up. So this is VDD. I just ran out of room to draw the PMOS like I normally draw it there.
Sure.
Okay? So, by the way, this whole structure here, that's just an inverter. Right? It's just an inverter off of the clock. It's just drawn in a little bit funny way. Okay? Okay, so just because I will actually give you the CML latch, let's see if we can figure out where hysteresis might exist in this latch. What would cause some potential hysteresis in this design here? Anybody see it? I'll maybe give you a hint. So let's say that previously you decided that VO plus was VDD and VO minus was VDD minus IB times R. Okay? So now, when the clock goes back high and I turn this thing on again, initially, what's going to happen? Or in fact, let's even maybe even ignore that. Let's even just pretend that we just turned both of these off during the time that we transition from this clock over to that phase. When we turn both of them off, what's going to happen at the output?
Goes to VDD.
Yeah, basically this side, VO minus, is going to start rising up towards VDD, right? Is it going to get there instantaneously? No, right? It's actually going to take some time. Of course, that time is just going to be set by the R and the C for you to exponentially settle towards VDD, right? Well, guess what? Even once I turn this thing on, still I have to settle out that residual decision I made from the previous cycle, right? That has a certain exponential time constant, which means that depending upon how many tau my clock cycle is, or my half clock phase is, I can actually predict exactly what the residual error from the previous cycle will still be, right? Because as long as these two aren't exactly both VDD, I'm going to have some residual, basically differential voltage offset at my output, right? Does that kind of make sense to everybody, or? So what this actually says, by the way, is that you have to build this latch in a way that you basically resettle the previous decision fast enough that you don't get a lot of hysteresis, right? That basically means these load resistors here have to be sort of relatively small. Now, by the way, that all sounds fun. What's bad about making those load resistors small? How does that hurt you?
Okay.
Yeah, I'm going to have small gain, right, in this phase. And in fact, there's even one more thing that's kind of bad about this. What happens with small load resistors when I flip to this phase?
Swing.
Okay, the swing is small, that's true. There's actually even something I'd claim, quote-unquote, even worse than that. What did we say sets the sort of time constant of the regeneration?
Let's see.
GMRL of the.
Okay, if you remember, we said that the time constant was set by the GM of this pair and the cap, right? Okay, now, we said that when we assumed we had current source loads. Okay, so if I looked at like the differential impedance of this structure right here, at DC, what did we say the sort of small signal differential impedance would look like? This is a weird answer, by the way. So, like if I move something up there and down here, how much current do I get flowing back out of this thing?
-1 over GM.
Yeah, it's a -1 over GM, right? So, by the way, the sign is not incorrect there. It really is a -1 over GM because it's in positive feedback, right? So it looks like a negative resistance. If you put more voltage onto it, right, it actually reinforces that, right? Okay, so if that thing looks like -1 over GM, remember when we said we were talking about the settling, we said the settling was going to be something like e to the t times GM over C, where again I didn't get the sign wrong because I had the negative GM in terms of my resistance, the -1 over GM as resistance. If I put a negative resistance in parallel with a positive resistance, what's going to happen? What do you guys think?
Could potentially be very large, right?
Ah, okay. So what you just said was if I have a negative R and then I put another R in parallel with it, that actually looks like an infinite resistance, right? That's actually correct. So now, in fact, remember when I'm in this phase, I actually want my resistance to be negative, right? So what would happen if this resistance, and let me call this R1 and R2. What if R2 is actually less than R1? Am I going to get a negative resistance? No, right? Because the parallel combination of the two is just going to look like a positive resistance. In other words, a normal resistance. Okay, so now I'll repeat the sort of original question then. So what's the bad news about these RLs needing to be relatively small in order to settle out the previous decision. What's it going to do to the effective GM we get from the whole structure in this phase?
It won't regenerate.
Well, okay, it's not that it won't regenerate, but basically
Long time.
I'll have less regeneration time. My regeneration time constant will be larger, right? Because my effective negative GM will go down because of the fact that I have these real resistors here, right? In other words, if the GM of this times the RL was only 2, I basically am going to lose half of my negative GM, right? So my time constant is going to be twice as large as it used to be, okay? So as I said, all these latches sort of have these trade-offs. With the CML, the biggest trade-off is really that if you want to make sure you have small hysteresis, that unfortunately means it's also going to take you longer to regenerate, okay? Because the two are just directly tied to each other in terms of how you have to choose that RL right there. Does this make sense to everybody? Or? Okay. So we talked some about hysteresis. Now, so you know sort of what it is. The key question is often, okay, so how am I really going to characterize that hysteresis? How am I going to know if my latch is sort of good enough from that standpoint? So in order to see that, what we basically need to talk a little bit about is essentially what's the sort of test that you should use to characterize the performance of your latch or your comparator, particularly from the standpoint of hysteresis. Now, the thing to keep in mind is that with hysteresis, because it's all about sort of memory and what happened in the past, basically what you have to sort of think about is how do you basically give the worst possible input into the comparator that will really exacerbate that hysteresis. And so the way you typically do this is with what's called an overdrive recovery test. So I'll just sort of draw the way you will do this. So basically, if I want to make sure that my comparator has kind of like the worst possible thing that I could have done to it in the past, what I should really do is essentially take the largest input signal I could possibly have, stuff it into the comparator, okay? Clock the comparator a whole bunch of times so that I'm sure it's gotten that input, so that it's resolved whatever the output should be based on that really huge differential input. And then all of a sudden, switch the polarity of the input to some very, very small residual voltage difference, but with the opposite sign, okay? And then clock the thing again, okay? So you can already maybe kind of see why I call this an overdrive recovery test, right? Because what I'm trying to do here is I drive the thing as hard as I possibly can in one direction for a whole bunch of cycles, and then all of a sudden for just one cycle, I want to see, will it resolve some really, really small input voltage, okay? So the way you actually do this test is you basically sweep this small delta V until you see the output of the comparator actually resolve the right way, okay? So let's just sort of see an example of what some of the typical waveforms would look like. So if I look at the output of the comparator, since I kept giving it, this really big differential input voltage, it should basically have all ones or whichever way I happen to do it. Here I happen to do it as a 1. So for all those previous things, it should keep giving me a 1. And if the comparator was perfect, then no matter how small of a delta V I gave it, right when I sample it here, it should go to 0, right? But in reality, what will happen is if you make that delta V too small, you'll see things that sort of look like this. So if you make it really, really small, it'll maybe glitch a little bit, but then just come back to where it used to be. If you make that delta V a little bit bigger, it'll maybe sort of go down a little bit farther and come back. A little bit bigger, it'll go down a little bit farther. In fact, you might even see it hang out at around VDD over 2 for a while, and then eventually maybe either come back or decide the right way, okay? So what you're really looking for here for this overdrive recovery test is what's the smallest delta V you can use, and make sure that your output, and I'll draw like a good trace. A good trace would obviously look like that, okay? So what you're really trying to do here is find what's the smallest delta V for which your output actually makes the right decision, okay? And by the way, not only does it make the right decision, but you want it to make the right decision before actually your next clock edge, right? Because even if it was eventually going to make the right decision, but already you've now gotten into the next bit, you've sort of lost the bit that you wanted, right? Does this sort of make sense to people, or? Yeah.
So is there any percentage, like how much it should have like settled to?
When you say how much it should have settled to, what do you mean?
Like once it regenerates, so
Okay. So you're sort of asking like, okay, if I got some waveform that looks like this and it started to do this and this was my clock edge, like right there, is that okay or not? That's kind of what you're asking, right? Okay, well, the answer is obviously it sort of depends, right? So depends on how you're using the thing afterwards. So most of the time, this would probably not be okay, right? Because remember, even after you've done your comparison, you probably want to do some logic or grab that data with another flip-flop or something like that and feed it into the rest of your system, right? So really it would be a question of, if you fed this particular data into your next stage, would it still have enough time to do whatever it's supposed to do? Okay? So I believe in the project specifically, I'll give you some specs by what I mean if it's okay or not. But usually it's pretty obvious. And by the way, particularly for these kinds of things, because it's a comparator and it's this regenerative structure, the difference between what it takes to have this and this could be incredibly small. Like, adding even, let's say, half a millivolt or smaller than that of extra input signal could give you the difference between that and that. Right? So from a practical standpoint, you'd probably quote it as what gave you something that actually resolves within, some reasonable quote-unquote amount of time. Right? Obviously, the more time you're willing to wait, the smaller you can make that delta V. Right? So as an example, if you had a lower speed comparator where your clock didn't arrive until over here, you could indeed probably resolve much, much smaller inputs. Right? But the whole thing is exponential, and so from a practical standpoint, probably once you've gotten, if this was already, let's say, 6 tau, and this goes to like 12 tau, okay, I mean, the numbers you're now talking about are really, really small, right? Yeah?
Comparator offset statistic. So you say if you can only resolve delta
so
V.
from the standpoint of practically how you're going to use this overdrive recovery test, obviously it can tell you not only what was the hysteresis, but also what was actually the offset of the comparator. Right? Because if you do this in the right way, if you do it in the direction that's sort of bad for offset, the comparator output won't flip until you've overcome both the offset and the hysteresis. So from the standpoint of sort of accounting for your bit error rate, that's exactly how I would use it.
Okay.
Right? I would basically say, okay, my offset's really not just my offset, but it's the offset plus the hysteresis. Okay? It's a great question. Any other questions on this, or? Okay, so by the way, just as sort of a side note, because it typically comes up in this, a lot of times when sort of people used to build these continuous time comparators that don't necessarily have these regenerative structures inside of them, one of the issues that you'd run into, and in fact you might even see this in your CML latch, is, let's just say I look at sort of the input stage of that latch there. If I really hit this thing with really, really big inputs, then my output is going to sort of be completely clipped, right? It's going to go completely to one rail or to the other. So it'll be, let's say, there and there. Now, if I'm really worried about sort of coming all the way back to looking at this very small input over here, what may happen is, because of these really big inputs that I put in the first place, I could essentially just end up having to slew the output back towards where it's supposed to eventually be, right? Particularly if I want to do this within a very, very short amount of time. So oftentimes what people will do, particularly in the designs that sort of look like this, is if you're really worried about sort of the overdrive recovery, what you might actually do is add a so-called clamp circuit. Okay? The idea of the clamp circuit is, and by the way, it'll often look something like that. So if that's like VO plus and VO minus, it's almost like sort of like a diode between the two sides, or actually two back-to-back diodes. the idea here is just, okay, if I'm worried about something like this overdrive recovery, let me just make sure that my swing is never so large that I actually have to sort of non-linearly slew back to where I used to be. Right? Let me just sort of clamp the swing at a spot where I know that even after I've gotten these really, really big input swings, it won't take me forever to come back and actually resolve these very small inputs again. Okay? Now, as I mentioned, for most of the sort of regenerative structures that we've looked at so far, you probably won't need to do something like this. But if you really had a continuous time comparator, meaning just a long chain of amplifiers, this can tend to be a pretty critical issue. Because you can imagine in each one of those sort of chains of amplifiers, if each one of them is railed all the way out, it can take you a really long time to basically slew each and every single stage and come back to where you're supposed to be. Okay? Does this sort of make sense to everybody? Or? Okay, so make sure you've got this down because, like it or not, you're going to be doing a lot of these overdrive recovery tests. Because as we were just talking about, this is really the only way you can figure out what's kind of like the effective quote-unquote offset or really the effective sensitivity of your comparator, and therefore to use that to decide how much input swing do you need to give the thing to get it to have a certain bit error rate. Okay? Now, if you thought that was the end of the story, unfortunately it's not quite it. Because there's, in fact, even more fun that you can get into when you sort of think about these comparators. So the last sort of thing that I'll spend a little bit of time talking about is basically this sort of so-called kickback issue. Okay, and conceptually, it's actually pretty easy to understand why you might be worried about something like this. So let's say just conceptually I have my comparator there, and I look at what's my input signal and my output signal. And so let's say, as an example, I have like a strong arm latch. Okay? So at the output, let's say my supply is VDD, and let's say that's 1 volt. So at the output, we know that basically the signal swing right here is going to be 1 volt, right? Well, at the input, let's say I maybe want to resolve like 1 millivolt kinds of signals. What's the really sort of nasty thing that could potentially happen? And imagine that, what's inside of that comparator box is almost just like a transistor, or the input goes to the gate and the output is the drain. What's the really bad thing that could potentially happen here?
GD.
Yeah, there we go, right? All it takes is a small little amount of capacitance from there to there. And unfortunately, this huge 1 volt swing can couple back and basically have way more than a 1 millivolt effect on the input, right? So in other words, I can basically just be in the process of deciding, in the process of sort of driving this towards the final voltage it's supposed to be. I could actually be creating glitches or errors all the way back on the input. And therefore, I could actually, unfortunately, make the wrong decision because of the glitch that I introduced. Okay? So, just to make it sort of clear why this is kind of a big deal, if I wanted to make sure that this this output has absolutely no effect on the input, or at least below the resolution that I care about, what kind of like attenuation ratio do I need from the output back to the input, roughly speaking?
More than 1,000?
Yeah, I need about a factor of 1,000, right? Because to get from a volt all the way down to a millivolt, that's a factor of 1,000. So in fact, I better make sure that however this output signal is, it has more than a factor of 1,000 attenuation by the time it gets back to the input. Okay? So Dan mentioned that this was maybe through CGD. Well, turns out it can actually be even worse than that. Okay, and let's take a look at how that can happen. So let's again just draw the input pair of the strong arm latch. Okay? And remember, I'm going to tend to want to, recharge or pre-charge that source node there up to VDD to get rid of hysteresis, right? So let's say that's my VI plus. That's my VI minus. Okay, so what's a great way to actually pick up to actually couple junk back onto Vi plus and Vi minus, just from what I've drawn here already. What sort of capacitor is going to tie Vi plus and Vi minus to things that are moving around with very large voltages?
CGS?
Yeah, CGS, right? Because guess what? I've got a CGS there. We've got another CGS there. And this node right here, like we just said, this whole thing here just looks like an inverter, right? So that thing is going to start at VDD and jump down to ground. Well, guess what? All of that basically charge is going to jump right back through CGS and dump a spike of current onto my inputs, right? Now, by the way, of course, it's not just CGS, because in fact, if you remember, those middle voltages also sort of start, those middle voltages also will start up near VDD, and of course there is a CGD there as well, and so those will also couple some charge back onto my inputs. Okay? So let's maybe sort of decompose this a little bit and see what kind of an effect this might have. So for the two parts that are coming through CGS right here, what kind of change is it going to cause on the inputs? Or at least ideally speaking, how do you think that sort of the inputs will, what will happen to those two inputs based on the fact that the center node here goes from VDD to ground? Well, first of all, just what direction should they move?
Down.
Yeah, they're going to move down. Okay, so now here's the key question. Are they going to move down differently on the two sides? Or are they going to move together down? What do you guys think?
Different.
Oh, okay, well, I think you have the somewhat sarcastic answer. Yes, they will be somewhat different, but if everything was perfect in my circuit, will they move together or differently?
Move together.
Yeah, they should move mostly together, right? Because if Vi plus is almost exactly the same as Vi minus, or really if it's exactly the same as Vi minus, and this transistor is exactly the same as that transistor, then both of them should move down by exactly the same way, right? It should be sort of a common mode glitch you introduce. Now, of course, the bad news is they're not the same, right? These two transistors are unfortunately never going to be exactly the same. We're going to talk a little bit more about that maybe today or next time. But actually, it's even worse than that. Because remember, the whole point of building this thing was I want to make sure that I can basically decide that Vi plus was larger than Vi minus, or vice versa. That means that these two input signals will be slightly different. If they're slightly different, then basically the characteristics of these two transistors will also be slightly different, right? I may have a ever so slightly different CGS there, right? Not only that, obviously, because these two were different, the edge rates on these two nodes will also be different, which then means that the amount you couple back onto the inputs will also be slightly different, right? So in other words, what this is kind of getting at is that even though maybe hopefully most of the kickback is common mode, and hopefully shouldn't cause an offset, in fact, you're always going to have some differential kickback, right? So it's always going to sort of dump some differential charge back onto the inputs. And so just like with the hysteresis, if you're not careful about, paying attention to what that kickback is, you might actually get incorrect answers, okay? Now, I sort of drew these as voltages here. In reality, there's no such thing as perfect voltage sources, right? So in fact, what really actually ends up mattering a lot is what was the output impedance of the thing that's driving those inputs, right? Because obviously if I have zero output impedance, then all of that charge just gets sucked into the voltage sources. But in reality, there's some output impedance there, okay? as we'll talk about in 1 second, the way you typically end up having to fix this is basically by building a little circuit that will have very, very low output impedance to drive the input of your comparator without getting really big glitches from this kickback effect. Okay? Does this kind of make sense to everybody? Or? Okay, so now, just as sort of a side note, because it's something you may eventually run into, I've mostly been talking about the comparator kicking back onto itself, but actually you can even have comparators kicking back onto each other. Okay, and to see why something like that might happen, let's sort of think about the following scenario. So right now in your project, you guys are looking at building like a 3 gigabit per second link, which means that your comparator has to run with a clock frequency of 3 gigahertz, right? In other words, it has about like 333 picoseconds to actually resolve. Well, so I don't know how many of you guys have sort of looked at this yet, but let's sort of see just, your gut reaction. Let's say that rather than running at 3 gigabits per second, let's say I told you that I actually wanted you to run at, I don't know, 20 gigabits per second. Okay? So if I want to run at 20 gigabits per second, what sort of like clock rate do I need in my comparator? If I just had one comparator receiving 20 gigabit per second data, how fast is that thing going to have to be clocked?
20 gig.
Yeah, 20 gigahertz, right? That means you've got 50 picoseconds to basically sample the input, amplify it up, and regenerate, and then reset everything, right? Well, so if you don't believe me, that's going to be tough. In your technology, that's going to be painful. Okay? Well, so it turns out you could, well, okay, by the way, I don't recommend this, but you could actually build a link that would operate at 20 gigabits per second, even in your technology. And you could actually get sort of fast enough throughput to do it. But the way you do it is actually you have to be a little bit clever. Okay? So as an example, let's say that rather than running one comparator, I say, okay, let me take my input signal and actually feed it to 2 comparators. But now what I'm going to do is I'm going to have each one of those comparators decide on opposite edges of the clock, right? So as an example, this upper comparator here decides when the clock goes high, and this lower comparator here decides when the clock goes low. Okay? Well, what's the good news about this? Now, since I've got these 2 comparators, each one of them can operate at half of the speed, right? Because I can make this a 10 gigahertz clock, and I'll get the 2 bits at the output. Basically, I'll get 2 bits for every 10 gigahertz clock cycle. Okay? So the good news here, obviously, is that I can actually build something that's much, much faster than the speed at which each one of these comparators is really running. Now, why do I mention this in the context of kickback? Well, we already talked about how, okay, every comparator has some coupling from its output back to its input, so it's going to kick back onto itself. But if you think about something like this, and let's just sort of draw the 2 clocks, whenever the clock for that first comparator goes high, the clock for the second comparator is going to be going low. In other words, when this one's right about to make a decision, this one here is going to be pre-charging. Okay? Well, remember, when you go into the pre-charge, you're sort of taking that full rail decision you just made and slamming it all the way back to the other rail, right? In other words, the kickback you get from that other comparator in the pre-charge phase could be a lot worse than the kickback you have from the comparator, from this comparator back onto itself. Okay? So these are called basically interleaved structures, or also sort of parallel or time interleaved structures. Anytime you have something like this with multiple comparators looking at a single input, kickback is even more of a problem. Because basically, now each one of those things can be kicking back onto this input voltage in a different way. And so the decisions you make are all sort of impacted by each other, right? Like, depending upon what this guy decides or had decided, that could have an impact on what you will decide this time around. Okay? So bottom line, kickback, if you can get rid of it, to the extent that you can, You really, really want to. Okay, especially if you're going to be doing things like this, which, by the way, is very, very common. Okay, so really the main trick we have to play to sort of mitigate that kickback, well, actually the two main tricks are, as I mentioned previously, we're going to want to somehow make sure that we drive the comparator with very low impedance, A, and B, probably what we want to do is find a way to sort of isolate the real input from the output of the comparator. Okay? So, what do you guys think? How can we sort of do something like that? What's a sort of very simple way to try and build something that will isolate the output of the comparator from the real input and give us a pretty low output impedance? Any thoughts?
Buffer it.
Buffer it, yeah, okay. So what is that buffer probably going to look like? How would you build that buffer?
That's a common drain state.
Ah, okay. So you said maybe we can do something like a source follower, right? Or really a pair of source followers. Okay, this sort of works. I claim is actually maybe not the best way of doing it, though. And there's actually a very specific issue that we have to be careful about here. So, this indeed will give you a reasonably low impedance, right? It'll look like 1 over GM. But remember, those glitches, particularly the common mode glitches, can be really big, right? So, if I'm trying to use a transistor, and so let's actually make this a very sort of specific example here. So let's say the thing sort of looks like this, okay? And I'm going to actually have, oh, sorry, let me draw it a little bit differently. Let's say it looks like this, and let's say I tell you that there's going to be a common mode change of 1 volt at the output over there, okay? So I'm going to get basically 1 volt coupling through those caps back into the outputs of those source followers. So, and let's assume that, okay, fine, I have maybe low impedance, but not super low impedance. What's going to happen when I couple a lot of charge back through those 2 caps, through those source followers? What's going to happen to their output impedance? Is it going to be exactly 1 over GM, or is it going to shift around? What do you guys think? By the way, when we say that the output impedance is 1 over GM, what are we sort of implicitly assuming?
RO is infinite.
Well, okay, the RO is infinite, that's true. I'm not even going to worry about that.
Frequency.
Sorry?
Low frequency.
Okay, that's low frequency. I'm not even going to worry about that either. Like, when you say GM, what is GM?
Small signal parameter?
It's a small signal parameter, right? It's just saying, okay, if I look at the derivative of something at that particular point, that's the slope I get, right? But actually, the real quote-unquote impedance there, it's some large signal quantity, right? It can actually vary as a function of what charge I kicked back onto there. Well, why is that bad news? Well, remember, these two are slightly different, right? If they're slightly different, that means the output impedance I see will be slightly different, right? Because these transistors, they're big nonlinear things, right? Well, if the output impedance of these two is slightly different, that means that even though I have a purely common mode kickback, take the same common mode current, feed it into 2 slightly different impedances, you'll get a differential input voltage, right? So, although this is actually not a bad idea in terms of trying to create a lower impedance, turns out you not only actually want a low impedance, you actually want an impedance that's very, very symmetric, that's very, very balanced on the 2 sides. Because if it's at all imbalanced, it'll convert the big common mode kickback into a differential kickback, okay? So, given everything we just said, now, how do you think you're going to want to build that so-called buffer? Any thoughts?
Something differential.
Okay, something differential. I agree with that. Any, what else do you want?
Cross couple them the way that we did before with like a pass transistor.
I'm not sure exactly how that would work. I mean, maybe you have an interesting idea that we should talk about it later, but I'm not sure exactly how that would work. By the way, the particular circuit I'm looking for here is just about the simplest, stupidest circuit that we've talked about, I don't know, about 30 times now, just in different contexts.
Resistively loaded.
There we go, resistively loaded. Okay, so now let's see, why did I say a resistively loaded amplifier? So by the way, people often refer to that as a preamp. So what's really nice about resistively loaded amplifier? Especially if this RL over here is small.
Low output impedance.
Okay, yeah, it's low output impedance. We said that was good. What else was important about the output impedance?
It's not a function of the transistor.
There we go. It's not a function of the transistor, or really, to be more specific, it doesn't depend on the output voltage, right? Because the whole problem with a source follower here is really coming about because even though I say that it's a 1/GM at a particular bias point, if I kick it away from that bias point, the output impedance isn't what I used to think it is, right? It's something else. If my impedance is really set by resistors, and as long as I do a reasonably good job in building those resistors, meaning the resistors are linear, it doesn't really matter exactly what the bias point is, right? So even if I kick back in a really big way on the common mode, as long as these resistors are very, very small in terms of impedance, relative to all of the stuff coming from the active transistors, the impedance on the two sides should be very constant, right? If it's very constant, that means that this kickback will have very, very small conversion into the differential mode, right? Because the only thing that causes that conversion is the mismatch in the impedance of the two sides, okay? Now, even this, of course, isn't perfect because the transistors have some RO associated with them. That RO will indeed vary with the actual voltage you put at the output. But as long as you make this RL very small in comparison, the variation will also be small in comparison. Okay? So with most sort of, I'll say, quote-unquote, good comparator designs, you will indeed want to add some sort of preamp like this. And it's not that you're really trying to get a lot of gain out of it, because, by the way, getting gain is tough, because, as we said, these have to be really small, and we want to make sure they're small relative to anything coming from the transistors. So, you'll get a little bit of gain out of those preamps, but it's really mostly to isolate yourself or really to eliminate all of the bad stuff that can happen if you get really big kickback onto your inputs. Okay? So if you remember sort of way back at the beginning of the lecture, I said that just about every comparator looks like some sort of preamp followed by a latch. Well, now you know why. Right? The preamp is really there to basically eliminate the effects of kickback. And the latch is really where you make the final decision. The latch is where you have that positive feedback embedded inside of the circuit. Does this sort of make sense to everybody? Or? Okay, so as I said, actually in the final phase of the project, you're going to get a real comparator. And so you're going to have to play with all of these fun issues. But so just to make sure it's sort of clear, the key thing you really are going to be needing to make a lot of use of is this overdrive recovery test. Okay, so you should really make use of that to understand what is the actual performance of your comparator, including all of these bad effects that we've talked about. So things like hysteresis, kickback, and so on and so forth. Okay, so unless there's any questions on this, let's maybe sort of just briefly dive into our next topic. Okay. So the next topic, which is actually one of the last things we're going to be talking about, is basically matching. And what I mean by matching is when I draw two transistors and say that they're the same, how much the same really are they? In other words, how identical can I really make any two transistors? Now, in cases it isn't obvious already, the reason you're going to care about this is generally, or even specifically in our project, if we looked inside of that comparator, right, we said we wanted that comparator to have basically as low of an offset as we possibly can, because we want to make sure that we get, the more the offset is, obviously the harder it is to meet our beta error rate specs. Well, that's almost always going to boil down to I have some sort of input pair And if there's any mismatch between that input pair, it'll translate into offset at the input of the comparator. Okay? So again, the question we're really going to be going after here is, how well matched can I make these two devices to each other? Now, we talked a lot about things like the layout and how we be careful about that. We'll kind of briefly review that here in a second. But it turns out even the stuff that is not just sort of the deterministic effects, things like you just made a mistake in your layout, actually, you can actually very well predict how much mismatch you should be getting from those transistors from a design standpoint. Okay? Even though, actually, as we'll see in a second, a lot of the mismatch you get is random, meaning you can't actually control it, but just like with noise, you can predict at least what would be like the variances that you're going to get from the mismatch. Okay? So again, just to sort of like get us all onto the same page here, we need to talk a little bit about just what are the different types of mismatch that could exist in basically ICs. And really, these categories are mostly sort of created based on sort of the spatial extent of the variations, okay, or the spatial correlation distance of the variations. So we'll see in a second, actually, most of the categories that I've written here, we're not going to care about too much. So let's just sort of see that. So the first category is the so-called die-to-die variation. So what I mean by this is, if I take like a wafer of chips, and I look at each individual chip, this type of variation means that on any given chip, basically all of the transistors on that chip kind of look the same to each other, but they all look a little bit different than all of the transistors on another chip, on a different piece of the wafer. Okay? So this type of variation, again, that's kind of saying like the spatial extent is the entire chip. Meaning if something is going to change, it's going to change over the entire chip. For most of the stuff that we're going to do, that's not going to be too big of a deal. Okay? Because, again, as should hopefully be obvious, if I'm really building a comparator and I really want these two things to match each other, well, okay, I guess as is really obvious perhaps, it's going to be on the same darn chip, right? Because otherwise I just don't even know how I built that circuit in the first place, right? So if both of them were shifting the same way, even if, an example, both of their thresholds went up by 100 millivolts, that shouldn't have too big of an impact on their mismatch. In other words, the offset that you would see at the input. Similarly, the next sort of category of mismatch we can see is so-called within-die variation. And here I've sort of put this in parentheses as long range. What I mean by this is that within like a certain section of the chip, all of the transistors look the same, but they look different than all of the transistors on a different section of the chip. Right? So just an example, I could have something like, if I took my die and I look at, one transistor here versus one transistor over there, in other words, in the two different corners, those two devices may not be exactly the same. Right? They may have some basically variation between them. But again, as we kind of talked about a second ago, if I really want to build, let's say, a comparator or an amplifier or whatever it is, and I want to make sure those two devices are very, very well matched to each other, well, it would have been a really stupid idea to put one transistor on one corner of the chip and the other transistor on the other corner of the chip anyways, right? Because if nothing else, I just have to have these huge wires and etc., right? If you really want them matched, you're going to put them as close together as you possibly can to each other, okay? So the real variations that we will definitely care about the most is these so-called local or short-range variations. So these are the things where basically every single device can be slightly different than the device right next to it. Okay? In other words, the sort of correlation distance in terms of that variation is much, much smaller than the dimensions of each individual device. Okay? And again, this is really the most important source of mismatch. Okay? So if you go and you like talk to the process people and you ask them sort of how much variation do you have, they'll usually quote you all of these lumped together. But the thing you care about the most is really this local variation here. Okay? So, trust me, there's lots and lots of ways you can pick up those local variations. Everything from just how you've done the layout to actually just how many atoms happen to be sitting inside of a particular transistor. But since we're sort of running out of time for today, I think we'll pick back up with that next time. So I'll see you guys then.